In part 3 of this introductory lecture on solutions, we'll talk a little bit about the temperature dependence of solubilities. That's something we started mentioning in the last slide of part 2 of this lecture. We'll also cover a little bit about the pressure dependence of gas solubilities in liquids, and then we'll finish with 3 example problems. So let's look at the effect of changing temperatures on solubilities. Common experience would tell you that increasing the temperature would often result in increasing solubilities. Think about how much better sugar dissolves in hot tea as compared to iced tea. Below is a graph showing the solubility of several ionic solids, many times called salts in general, ionic salts, in water as a function of temperature. So we have solubility in grams of salt or grams of ionic compound in 100 grams of water versus temperature in degrees C. Well, what are some things to note about this? It appears that there are indeed a number of examples where solubilities increase significantly with increasing temperatures, at least for these ionic solute examples. In fact, it appears that the solubilities are increasing for all the examples here except for one. Now, the extent of the temperature dependence does seem to vary considerably. So, for example, if we compare potassium nitrate, this green curve, where the solubility increases drastically from close to 0 to 50 degrees, about a factor of 6, with sodium chloride, which barely increases in solubility as you increase the temperature over the same range, around 0 to 50, and even beyond, it doesn't seem to increase in solubility that much. So most of the examples show an increase in solubility with temperature increase, although the extent of that increase can vary considerably. And then there's cerium sulfate, a real problem. Now we can look at the data in this table through the lens of our previous analysis, where we talked about the fact that the overall free energy change, delta G, for the solution process is equal to the overall enthalpy change minus T, absolute temperature, times the overall change in entropy, delta S of solution. In this equation, you can see that delta G of solution is clearly temperature dependent. There's a T right in the equation. However, the delta G of solution will become more negative. In other words, we would expect higher solubilities, more favorable solubilities at higher temperatures, only if delta S of solution is positive. If delta S of the solution is positive, then increase in the temperature is going to make delta G of solution more negative. And it seems reasonable to assume that most ionic solids, when dissolving them in water, will result in increased disorder. So delta S of solution being positive, for most cases, is not too hard to believe. So what's the deal with cerium sulfate? Well, cerium 3+ is a very highly charged cation. And highly charged cations can actually have an overall ordering effect in aqueous solution. And of course, this is not the only ion going into solution here. We also have sulfate. But when the ions have very high charges, it's possible that the overall delta S of solution is actually negative. In other words, the highly charged ions actually organize the water molecules around them so strongly that when they go into solution, they actually create order. So if this was the case here with cerium sulfate and delta S of solution was negative, then increasing the temperature is actually going to make delta G of solution more positive. Situation with cerium sulfate might be more complicated than this, just because you'll notice that there's kind of a strange temperature dependence. So it the solubility does decrease with increasing temperature, but then it kind of levels off and doesn't change very much for most of the way between about 30 and 100 degrees C. Now, as opposed to many other solute-water combinations, gases, when they're acting as the solutes, in other words, you're trying to get gases to dissolve in liquids, we're going to talk specifically about water. Gases have decreased solubilities in aqueous solution as temperatures increase. Below is a graph showing the solubility of several gases in water as a function of temperature. You want to note about this solubility graph here is that the solubility, instead of being given in grams per 100 grams of water, is just given in millimoles. That would be 0.001 moles per liter of water. And the data is collected in a way that the experimental conditions are set so that there's a 1 atmosphere pressure of the gas maintained over the water, over the solution, as the temperature is increased. But the biggest thing to notice here is that all of these gas solubilities decrease with increasing temperature, and they decrease by varying rates. So what do we observe? Well, the extent of the temperature dependence, as I just said, does vary with the identity of the gas. There are no exceptions shown. That is, there are no instances where the solubility of a gas increases with increasing temperature. And I guess we just have to state that as a general premise that you can pretty much expect that, since we're only showing 4 gases here. There are some notable and perhaps more interesting gases missing from this diagram. For example, carbon dioxide, sulfur dioxide, nitrogen dioxide. So why are these missing from here? Because they're fairly common gases, at least in the laboratory. Well, these 3 gases, for example, don't just dissolve in water, but they actually react with water to form additional chemical species and complex equilibria. So for example, when carbon dioxide goes into water, it just doesn't simply form aqueous carbon dioxide. It can undergo a reaction with water molecules to form carbonic acid, which then turns out to be in equilibrium with a small amount of bicarbonate and hydrogen ions. That's why carbon dioxide being dissolved in water forms a weakly acidic solution. Now, the solubility of CO2 gas still does decrease with increasing temperature. We're not showing it on this chart, but not in a way that's directly comparable to the 4 gases in the diagram on the left, since none of these are literally reacting with water. We can look at this data also through the lens of our equation, delta G of solution equals delta H of solution minus T delta S of solution. It's reasonable to assume that a gas, which is very disordered, dissolving in water, essentially becoming trapped in the liquid, would involve a decrease in disorder. That is, we could probably reasonably assume that delta S of solution for gases dissolving in water would be negative. That would be an increase in order. Well, if delta S is negative, that means if temperature increases, it would make the minus T delta S term more positive, making delta G of solution more positive, making the gases less soluble in water as the temperature increases. While we're on the subject of gases, we also want to take a look at the effect of changing the pressure on solubilities of gases in liquids. Again, we'll work primarily with water. Overall, the solubility of a gas in a liquid can be described by Henry's law. The solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above that liquid. So we have an equation, capital S subscript gas, that's the solubility of the gas in the liquid. This would be in units of moles per liter, that is molarity. K sub H here is Henry's law constant. The units would be molarity per atmosphere, and the value depends on the nature of the individual gas and the solvent, and of course the temperature. And P subscript gas is the partial pressure of the gas over the liquid in atmospheres. Basically here, if the partial pressure of the gas over the liquid goes up, then the solubility of the gas in that liquid goes up. Here's an example problem. What pressure of carbon dioxide is required to maintain a total concentration of dissolved carbon dioxide of 0.14 moles per liter in water at 25 degrees C? Well, this is a straightforward calculation, providing that you have a table of Henry's law constants handy, which, by coincidence, we do. So we have solubility of the gas in this case is equal to Henry's law constant times the partial pressure of the gas over the solution. What we're interested in is this partial pressure. So we solve for that. We put in the solubility of the gas that we're shooting for, 0.14 molar, and we divide by Henry's law constant for CO2, 0.034 molar per atmosphere, and we get 4.1 atmospheres. So this would be the partial pressure of carbon dioxide required to be maintained over the solution in order to keep the total dissolved carbon dioxide at a concentration of 0.14 molar. Now, just as an aside here, molarity was covered as a concentration unit in General Chemistry 1. We'll cover it again in this module along with some other concentration units. You want to note here that Henry's law constants are experimentally determined values and reflect the total concentration of dissolved gases in all its forms, even forms resulting from the actual reaction of the gas with water. So therefore, gases such as CO2 and ammonia are listed alongside gases that simply dissolve in but do not react with water. Remember, on the previous slide we had a graph of the solubility of gases in water. None of those gases actually reacted with water, so CO2 wasn't on that graph. In our table of Henry's law constant, CO2, which reacts with water, is included, along with ammonia that reacts with water. But the Henry's law constant gives us a feel for the total dissolved gas in the water in all its forms, even in forms that have been created by the reaction of the gas with water. So if you look at a Coca-Cola can, on average, the 12-ounce soda can sold in the US tend to have a pressure of roughly 120 kilopascals of CO2. That would be about 1.2 atmospheres over the solution, over the soda, when canned at 4 degrees C. And if you allow the can to come up to close to room temperature, the pressure increases, of course, because at the higher temperature, CO2 wants to escape from the solution. It's less soluble, so the pressure builds up above the solution of the soda in the can. Interesting thing here is that you're actually doing two things at once here. If you let the temperature go up, CO2 escapes and increases the pressure of CO2 in the sealed can, but the increased pressure of the CO2 would tend to force it back into solution. So what you end up doing is reaching kind of an equilibrium state where the pressure builds up at the higher temperature. Let's look at a few example problems that hopefully will illustrate some of the principles we covered in all three parts of this lecture. Here's the first question. The drawings below are representations of the structures of vitamin D3, that would be on the left here, and folate, that would be on the right. Now, using the like dissolves like method, give an explanation as to why vitamin D3 is fat soluble, whereas folate is a water soluble vitamin. And as a little hint here, fat is a general description of a class of molecules that have very long chains of carbon-hydrogen, carbon with 2 hydrogens, and carbon with 3 hydrogen groups. That is, having structures similar to that of hexane, but involving much longer and more complex chains. We also want to note something else about these drawings. I left off the unpaired electrons, I should say not unpaired, the lone pairs of electrons that you'd normally see on oxygen and on nitrogen. Well, if you look at folate, folate has 2 OH groups. There's one here and one here. It has 3 NH groups. There's one here and here and here, and one NH2 group, and also 3 nitrogen atoms. That would be a lone pair on this nitrogen. 1, 2, 3. These sites would all allow for very strong intermolecular forces, primarily hydrogen bonding, between folate and water, thus making folate water soluble. On the other hand, vitamin D3, which does have one OH group, and it's right there, even though it has just one, it has one OH group, the bulk of this molecule really consists of just carbon-hydrogen chains. Carbon chains with hydrogens attached to the carbons at various points. So therefore, vitamin D3 does not have strong intermolecular interaction with water, and it does have a lot in common with fats. Fats would contain long carbon chains like those found in most of vitamin D3. So vitamin D3 is fat soluble, folate is water soluble. Here's a second problem or question. Acetonitrile, CH3CN, dichloromethane, CH2Cl2, and cyclohexane, C6H12, are all organic compounds, meaning carbon-based compounds, that exist as liquids at room temperature. And below are both 2D Lewis structures, including this time lone pairs of electrons, and 3D ball and stick figures representing the 3 molecules, acetonitrile, dichloromethane, and cyclohexane. It turns out that acetonitrile is miscible with dichloromethane, so these two liquids mix quite nicely. But acetonitrile is not miscible, does not mix well with cyclohexane. So how can this be explained using an analysis of the types of intermolecular forces at play here in the concepts covered in this lecture? So let's take a little closer look at the structures of these 3 molecules. If you look at acetonitrile and you see the shape of the molecule and the fact that there's a very electronegative nitrogen at one end, it's probably not hard to believe that this is a polar molecule. And so the intermolecular forces holding acetonitrile molecules together or attracting one acetonitrile molecule to another in liquid would consist of dispersion forces and dipole-dipole forces. Now likewise, dichloromethane, because of its 3D shape and the placement of the 2 fairly electronegative chlorine atoms at one end of the molecule, also make this a polar molecule. So it would have dispersion forces and dipole-dipole forces operating. However, with hexane, which is simply a cyclic carbon chain, we have a nonpolar molecule with only dispersion forces operating between its molecules. Therefore, the like dissolves like principle would explain why acetonitrile is miscible with dichloromethane, but it is not miscible with hexane. Let's look at one more example problem. The Handbook of Chemistry and Physics lists the solubility of lithium fluoride as only 0.134 grams per 100 grams of water. Now that same reference, the Handbook of Chemistry and Physics, lists the enthalpy change of this for solution, delta H of solution for lithium fluoride as slightly endothermic, in other words, a small positive number. The positive delta H of solution could be used as a reason for the low solubility. However, if you recall, the delta H of solution for sodium chloride, which as you know is quite soluble at 36 grams per 100 grams of water, the delta H of solution for that is also slightly positive, 3.88 kilojoules per mole. These two values are fairly close. So what we'd like you to do here is use an energetics argument, meaning use the equation delta G equals delta H minus T delta S to rationalize how lithium fluoride could be so much less soluble than sodium chloride in water, despite the two solids having very similar delta H of solution values. Well, here's how we might approach this. We'll put a box here with the lithium fluoride dissolving in water on the left, and on the right, sodium chloride dissolving in water. The analysis we're going to do here is very similar to that which we did for ammonium nitrate versus sodium hydroxide and sodium chloride versus silver chloride on previous slides. So let's look at the case for lithium fluoride. Remember, this is the ionic compound that's not very soluble in water. The low solubility of the lithium fluoride means that delta G of solution is either positive, or if it's negative, it's not very negative, pretty close to zero. We know that the delta H of solution is positive, 4.73 kilojoules per mole. Temperature is 298 K. We're doing this at room temperature. So what about delta S here? Well, the delta S of solution, if positive, would be a very small positive number. If this was actually positive, which happens a lot, remember, for ionic compounds dissolving in water, if it were positive, it would have to be a very small positive number, because if it was too positive, it would make this term too negative, overwhelming this positive delta H and making this significantly negative. We know this can't be significantly negative. So if it's positive, it would be very small. If we say, well, you know, it would have to be so small that maybe it's silly, maybe we should just assume that it's negative. And maybe it wouldn't be unreasonable to assume that delta S is negative, which would make this whole term positive, which would reinforce a positive delta G, making this not very soluble. Well, how could delta S here be negative? In other words, how could order be created? We alluded to this earlier when we talked about cerium sulfate. And again, it might seem strange that lithium ion and fluoride ion randomly distributed in water could actually create more order than existed in the pure water and the solid lithium fluoride before solution. However, lithium ion, even though it only has a +1 charge, is a really tiny ion. And tiny ions, their charges can have an outsized impact on the environment around them. Fluoride is another one that doesn't have a very high negative charge, but it's a very tiny ion. And so these ions, since they're so small, can have an effect like a very highly charged ion, maybe like cerium 3 plus or iron 3 plus, and when dissolved in water might be quite capable of ordering many water molecules around them and often initiating some significant additional reaction. So this is a long-winded way of saying that delta S could very well be negative here, which would reinforce a positive delta G. And that would help explain why lithium fluoride's not very soluble in water. Let's look at sodium chloride, which we've looked at before. We know that delta G a solution is fairly negative. We know that delta H a solution is positive. So we know that delta S has to be positive in order for the minus T delta S term to overwhelm this positive term and make this fairly negative, which we know it is because sodium chloride's pretty soluble in water. So what we'd say here is that when we compare lithium fluoride with sodium chloride, even though the two of them have very similar delta H solution values, the sodium chloride is a lot more soluble, probably because the delta S of solution for the sodium chloride dissolving is much more favorable. In other words, much more positive for the dissolving of sodium chloride than it is for lithium fluoride, and this would be the basis for the difference in the solubilities.